Welcome to 8.4, the trigonometric form of complex numbers. We've seen complex numbers before, back in I think it's 1.7, 1.8. But now we're going to see how they look on the graph. So we can graph a complex number a plus bi by plotting a on the x-axis, that's the real part is on the x-axis, and b, the imaginary part, is on the y-axis. Okay. So x-axis is for real numbers, the y-axis is for imaginary numbers. So the xy plane is then called the complex plane. I want to underline that in your notes or highlight it. Okay, graph the following complex numbers. 2 plus 3i, so 2 plus 3i, so this is the I, up this way. That's A, 2 plus 3i. 4 minus 5i, so it's 4. The minus 5i goes down here, it's negative. That's B. And then C is negative 2 minus I. So negative 2, you're going to come over here, negative on the x-axis. Minus I means it's going to go down 1 on the y-axis. That's our C. That's the graphing of those. Okay, I'm going to scroll the screen. Next concept, the magnitude of a complex number. We say the magnitude of complex number z equals a plus bi, also known as the modulus or absolute value of c, is the real number. The absolute value of modulus of c is the square root of a squared plus b squared. Notice there's no I here. There's no I with that b. So it's just whatever b as we square that. And we use the magnitude of z to denote this non-negative quantity. Determine the magnitudes of the following complex numbers. Okay, so the magnitude of this is going to be the square root of negative 1 squared plus 3 squared. That's going to be the square root of 1 plus 9, square root of 10. And for negative 6 minus I, this magnitude is going to be the square root of negative 6 squared plus negative 1 squared. 36 plus 1, 37. Okay. Go to the next page, so feel free to pause. So for example 2 here, we're going to sketch z1, z2, z1 plus z2, and z1 times z2 on the complex plane. And z1 and z2 are not written, so z1 is negative 1 minus 2i, and z2 is 4 plus 4i. So negative 1 minus 2i, and z1. 4 plus 4i, that's z2. Then we want z1 plus z2. That's negative 1 minus 2i plus 4 plus 4i. Now we're going to add the real parts, add the imaginary parts. That's going to be negative 1 plus 4 minus 2i plus 4i. So I have 3 plus 2i. So 3 plus 2i. This is z1 plus z2. Now we want z1 times z2. That'll be negative 1 minus 2i times 4 plus 4i. We can FOIL this out then. Negative 1 times 4, negative 4, minus 4i, minus 8i, minus, check this out, 8i squared. So it's negative 4 minus 12i, minus 8 times negative 1, because I squared is negative 1. So negative 4 minus 12i plus 8 So it's 4 minus 12I. This is not drawn big enough, so 1, 2, 3, 4, 5, 6 further down. And it's 4 minus 12I, so 4 minus 12I. This is Z1 times Z2. Okay, feel free to pause that one. Now graph the region of the complex plane defined by the following. Z such that 1 is less than or equal to Z, less than or equal to, the magnitude of Z, excuse me, less than or equal to 4. And so recall that the magnitude of Z is the square root of A squared plus B squared. So Z squared is equal to A squared plus B squared. This, in a way, resembles x squared plus y squared equals r squared, and that's the equation of a circle. So our radius then for this circle is going to go from 1 to 4. So we have a radius of 1. So it's greater than or equal to this up to 4. And here's our shape. Looks like a big donut. Okay. So that is the magnitude of Z being between 1 and 4. So we've seen just A plus BI. We can also see there's a trigonometric form of this. If Z equals A plus BI, then the trigonometric form of Z is given by Z is the magnitude of Z times cosine theta plus I times the magnitude of Z sine theta. Or the magnitude of Z times cosine theta plus I sine theta, where the magnitude of Z is square root of A squared plus B squared, and theta satisfies that tangent theta is B over A. The angle theta is called the argument of Z. Just be careful about which quadrant you're in when you're doing this, because the arctangent is going to produce values from negative pi over 2 to pi over 2. But it could be in the quadrant 3 or quadrant 2 or 3, I should say, not just 1 or 2, 1 or 4. Now let me draw a little picture here to reference this. So this is Z. Here's your magnitude of Z. This is B, this is A. And here's your theta. So B is the magnitude of Z times sine theta, and A is the magnitude of Z times cosine theta. In this, again, tangent theta is B over A, that's Y over X, and theta is arctangent, or tangent inverse, of B over A. Okay, let's do an example with this. Write the following complex number in trigonometric form. So I want to take a look at this where it's graphed, and that'll give us a good impression of what the theta should be. We have 5, 1, 2, 3, 4, 5 minus 3i. Okay, so we'll get our theta there. So the magnitude of Z is going to be the square root of 5 squared plus negative 3 squared. That's the square root of 25 plus 9, or the square root of 34. Now tangent theta is going to be b over a. So tangent theta is going to be negative 3 over 5. Theta would be arctangent or tangent inverse of negative 3 over 5. If we put that in our calculator, make sure it's in radian mode. Get negative 0.54042. So we could write our z, and this is the right quadrant for it, so we're good with that. Z is going to be the square root of 34 times cosine of negative 0.54042 plus I sine of negative 0.54042. Okay. So that's going from standard form to complex. Now we're going to go to trigonometric form. Write this complex number in standard form instead of trigonometric. Now in this, do you see any coefficient for cosine or sine? The answer is no, so the magnitude of z must be 1. Our a is going to be just that 1 times cosine pi over 3, which is 1/2, and b is going to be 1 times sine of pi over 3, which is going to be square root of 3 over 2. So this cosine pi over 3 plus I sine pi over 3 is going to be 1/2 plus I times the square root of 3 over 2. Now, if you haven't had enough in terms of formulas, I have another one for you. It's called Euler's formula. I know it looks like it's Euler's. It's pronounced Euler's. It's one of those things that if you know someone's taking math classes, if they know how to pronounce this. So I'm just saying that if you go to a party and show someone this and they say Euler's, you can say, no, that's Euler's. And anyway, it'll be an inside joke. So e to the I theta is cosine theta plus I sine theta. That's e to the I theta. So if you had z equals the magnitude of z times cosine theta plus I sine theta, you could write this as the magnitude of z times e to the I theta. That's Euler's formula. Product and quotient of complex numbers. If z1 is z1, the magnitude of z1 cosine theta 1, I sine theta 1, and z2 is magnitude of z2 cosine theta 2 plus I sine theta 2. z1 times z2 is their magnitudes times, now this is where it gets cool, cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2, where their quotient will be the quotient of their magnitudes times cosine of theta 1 minus theta 2, I sine theta 1 minus theta 2. Not what we really expect, because they have a plus in here for our product and minus in there for division, a quotient. Let's go on to example 6. Perform the following operations and show the answer in both trigonometric form and standard form. Okay, so our magnitude here is 3. We have magnitude 3 cosine 180 degrees plus I sine 180 times 4 cosine 30, should say plus I sine 30. So to multiply these, we have 3 times 4 times cosine of 180 degrees minus 30 degrees, or plus 30 degrees, excuse me, plus I sine 180 degrees plus 30 degrees. So that's 12 times cosine of 210 degrees plus I sine 210 degrees. So that's 12 times what? Cosine of 210. It's going to be negative square root of 3 over 2. Plus I times sine of 210 is negative 1/2. So we end up with negative 6 root 3 minus 6I. So these are the two answers that they want. Okay, for the next one, we're going to perform the division that's going on here. So we're going to have 8 divided by 4. It's 2. It's cosine 135 degrees plus I sine 135 over cosine 30 plus I sine 30. So that's going to be 2 times, we're going to be subtracting these. Cosine of 135 minus 30 plus I sine of 135 degrees minus 30 degrees. So it's 2 times cosine of 105 degrees plus I sine of 105 degrees. Now unfortunately, the 105 degrees is not a standard value that we know. So here's the trigonometric answer. If we want the answer in standard form, we're just going to have to plug that in the calculator, make sure it's in degree mode, and we end up with 2 times negative 0.2588 plus I times 0.9659, and that's going to be negative 0.5176 plus 1.9319I. Okay. Okay, feel free to pause that. So we talked about Euler's formula just a few minutes ago. So recalling that formula here, z equals the magnitude of z cosine theta plus I sine theta, which is the magnitude of z e to the I theta. So applying this product and quotient rule for complex numbers, we get z1 times z2 is z1 e to the I theta 1, z2 magnitude e to the I theta 2. It's going to be the product of their magnitudes times e to the I theta 1 plus theta 2. And for division, you get the quotient of the magnitudes e to the I theta 1 minus theta 2. It's not too different from what we saw before. We can graph a complex number in the form z equals z magnitude e to the I theta by using polar coordinates. So in this, effectively, z is the r and theta is theta. So we can represent this using polar coordinates. So we're going to plot both complex numbers and on the same graph plot their product. So 5e to the 5 pi over 3. Let's see, 5 pi over 3, this is pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3 is here. This is 4 pi over 3. 5 pi over 3 is here, and it's 5. There's 5 e to the 5 pi over 3I. And then e to the pi I. So that means the radius is 1. Pi is over here. There you go. E to the I pi. And we want to get their products. So this first one is our z1, z2. So for z1, it has a magnitude of 5. And our theta 1 is going to be 5 pi over 3. For z2, its magnitude is 1, and theta 2 is going to be pi. So z1 times z2 is going to be 5 times 1 e to the I 5 pi over 3 plus pi. 5 e to the I, that turns out to be 11 pi over 3. No, that's not right. There's 3 over 3 plus 5 pi over 3 is 8 pi over 3. Okay, so let's think about where that is. Well, if we go around one full time, that's 6 pi over 3 because that's 2 pi. So then here's 7 pi over 3, 8 pi over 3. And it goes out to here. 5e to the I times 8 pi over 3. That's our z1 times z2. Okay. Let's step out of the way here and a little more scrolling. Feel free to pause that. Okay, clear the board. Powers of complex numbers, de Moivre's theorem. Given z equals z, magnitude z cosine theta plus I sine theta, and a positive integer n, z to the n, is the magnitude of z to the n, cosine n theta plus I sine n theta. Using Euler's formula, z to the n is the magnitude of z to the n, e to the I n theta. So use de Moivre's theorem to calculate square root of 2 over 2 plus square root of 2 over 2i. If we graph that, it's going to be up here, the first quadrant. So if we said tangent of theta is square root of 2 over 2 divided by square root of 2 over 2, so tangent theta is 1, theta must be pi over 4. And if we look at the magnitude of z, that's going to be the square root of square root of 2 over 2 squared plus square root of 2 over 2 squared. The magnitude of z is going to be the square root of 1/2 plus, 2/4, which is 1/2 plus 2/4. That's 4/4, which is square root of 1, which is 1. So we can rewrite z as 1 times cosine of pi over 4 plus I sine of pi over 4. So if we do the magnitude of z, or just z to the n, that's going to be 1 to the n times cosine, and we wanted n to be what, 22? Ooh, z to the 22 is 1 to the 22 times cosine of 22 times pi over 4 plus I sine of 22 times pi over 4, because our n is 22. So z to the 22 is going to be 1 to the 22 is just 1. This is cosine of 11 pi over 2 plus I sine of 11 pi over 2, if you reduce that. So where is that? Here we're at pi, 3 pi over 2, 5 pi over 7 pi over 2, 9 pi over 2, 11 pi over 2, down there. That'll end up being cosine of 11 pi over 2 is 0 plus I times sine of 11 pi over 2 is negative 1. So we get negative 1 from this result. But if you want to keep it in the other format, in the trigonometric format, there you go. You could also look at the same thing, by the way. What is this going to be if you just want to go between 0 and 2 pi? That's the same thing as being at 3 pi over 2. So you could also say z equals cosine of 3 pi over 2, which we all know is 0, plus I sine of 3 pi over 2, which we all know that's going to be negative 1. So if you did evaluate that, it's equivalent because it's a cyclical function. Okay, looks like we're on the last page of this section. We talk about roots of complex numbers. Given the non-zero complex number z equals the magnitude of z cosine theta plus I sine theta and the positive integer n, here's where it gets a little different. W sub k is z, this is for doing the nth root, z to the 1 over n cosine theta plus 2k. I know we're switching things up. We've got k's in here now. We didn't have k's before. Theta plus 2k pi over n plus I sine theta plus 2k pi over n defines n distinct nth roots of z for k being 0, 1 through n minus 1. So that means if you're doing the 4th root, k would be 0, 1, 2, 3. If you're doing the 5th root, k is 0, 1, 2, 3, 4. Alternately, w sub k, this is the Euler format, the magnitude of z to the 1 over n, e to the I, theta plus 2k pi over n. And again, this generates different values. K would be 0, 1, 2, for however many you need to do given what n was. Okay, so find the indicated roots of the following graphically represent each set of the complex on the complex plane. We want the 4th roots of negative 1 minus 1. Now, on a real plane, this would be impossible to do. We couldn't do this on the real plane. This is just, it's not real. It's complex. So on the real plane, it's easy to say, not possible, but we are growing past that, and we have the ability to learn how to do this now. So first of all, our magnitude of z is going to be the square root of negative 1 squared plus negative 1 squared. Negative 1, I know that's I, but its coefficient is negative 1. That's the square root of 2. So the magnitude of z is 2 to the 1/2. Let's talk about this location. Negative 1 for the real, negative 1 for the complex, so it's down here. Tangent of theta is negative 1 over negative 1, which is 1. And normally we think that is pi over 4, but given this quadrant, theta must be 5 pi over 4, excuse me, not 3 pi over 4. So we can represent this as, so our roots, it's going to be 2 to the 1/2 to the 1/4 times cosine of 5 pi over 4 plus 2k pi over 4 plus I times sine 5 pi over 4 plus 2k pi over 4. So this is the general solution. We're going to use k being 0, 1, 2, and 3. Start with k being 0. I think I'm going to need more space than that, so I'm going to erase this part, so hopefully you have that written down. Get rid of this too. Okay, so k equals 0. Let's talk about what that means for the angle. The angle is just going to be 5 pi over 4 plus 2k times, 2 times 0 times pi, and all this is over 4, so we get 5 pi over 16. For k being 1, we have 5 pi over 4 plus 2 times 1 times pi all over 4. That's going to be 13 pi over 4 over 4. That's 13 pi over 16. For k being 2, we have 5 pi over 4 plus 2 times pi all over 4. That's going to be, let's see, what's the next one? 21 pi over 4 over 4, or 21 pi over 16. And then we have k equals 3. 5 pi over 4 plus 2 times 3 times pi, all that's over 4. That's going to give us 29 pi over 4 or 29 pi over 16. So if we want to look at this, this might be easier to see if we do WK being 2 to the 1/8 e to the I times 5 pi over 4 plus 2k pi, that's all over 4. If we see it in this Euler's format instead, our W sub 0 is going to be 2 to the 1/8 e to the I times 5 pi over 16. W1 is going to be 2 to the 1/8 e to the I times 13 pi over 16. You might see a pattern of how much this is increasing by. W2 is going to be 2 to the 1/8 e to the I times 21 pi over 16. And W3 is going to be 2 to the 1/8 e to the I times 29 pi over 16. So we're going to go ahead and graph these around. And in this, I'm going to count out to here to be 1, 1, negative 1. Actually, I should have done a polar graph here. In a polar graph, we just have radius being a positive value. So in our first one, W sub 0, 2 to the 1/8. 2 to the 1/8 is approximately 1.09. So it means we're going to have an angle of 5 pi over 16. And right about here. This is W sub 0. W sub 1, it's 2 to the 1/8 e to the I, 13 pi over 16. So 13 pi over 16 comes out to be a little over here. W2, 2 to the 1/8 again, e to the I pi 21 pi, e to the I 21 pi over 16. So looking at down here. This is an approximation. It's W, I'm sorry, it's right down here. That's W2. This is our original Z right there. And the last one is going to be, that's where one should be. And the last one should be looking at 29 pi over 16, just under 2 pi. So it's right around over here. It's W4. W3. Okay, so that is taking the fourth root of a complex number. A lot involved with this one. I will admit this is probably one of the more challenging things of this section. We've got one more of these coming up here. So probably the most challenging part of the section. I'm with you on that. Okay, so feel free to pause that. I'm going to go ahead and go on to example 10, the last example of this section. So in this one, we're going to solve the equation z to the fourth plus 81i equals 0. And if this was any class before this one, you'd say that's not possible. We can't solve this equation, but we have the skills now. So z to the fourth equals negative 81. So z is going to be the fourth root of negative 81i. I forgot the I. So z is going to be fourth root of negative 81, well, let's say 81 times negative I. Now what's different about this one than the last one, we don't have the, doesn't feel like we have as much information from which we can proceed here. But we can think about this for a second. Fourth root of 81 times the fourth root of negative I. Fourth root of 81 is 3 times the fourth root of negative I. What I want you to take from this right now, I don't see a real part, I see just the imaginary part. Think of this as 3 times the fourth root of 0 plus negative 1 times I. So that whatever our theta is, we have cosine of theta equals 0 and sine of theta equals negative 1. So for which values is that going to be the case? When is cosine going to be 0, but sine's a negative 1? Well, that's whenever theta is 3 pi over 2. Okay, so what we have then is let's look at our different k's. In the fourth roots, we have k equals 0 through 3, k equals 0. I guess we have two choices. We could do 3 pi over 2 or we could do negative pi. I'm going to go for 3 pi over 2. What we have then is, in this case, it's going to be 3 pi over 2 plus 2 times 0 times pi all over 4. That becomes 3 pi over 4. Now, if I would have started with negative pi over 2, this would have been negative pi over 4. But so my point is there's more than one answer that would be acceptable. For k being 1, we have 3 pi over 2 plus 2 times 1 times pi all over 4. So 3 pi over 2 plus 2 pi is 7 pi over 4. 7 pi over 2 over 4. Oh, that should have been 3 pi over 8, shouldn't it? Yeah. 7 pi over 8. For k being 2, we have 3 pi over 2 plus 2 times pi all over 4. So 3 pi over 2 plus 4 pi, that'd be 8 pi over 2, so what we have is 11 pi over 2 over 4. So 11 pi over 8. You see the pattern yet? It goes up by a 4 in the numerator every time. So k equals 3 pi over 2 plus 2 times 3 times pi, all that over 4. That's going to be 15 pi over 2 over 4, or 15 pi over 8. So our solutions, we have w sub 0. It's going to be 3 e to the 3 pi over 8i. w1 is going to be 3e to the 7 pi over 8i. w2 is going to be 3e to the 11 pi over 8i. And w3 is going to be 3e to the 15 pi over 8i. And these are all the solutions to this equation. And that's going to be it. That's the end of 8.4. I know it's kind of a long section, 6 pages, and then some pretty heavy stuff at the end. So you might want to watch it a second time. And we'll call it good for today. Thanks. Bye.